I'm going to prove one of my favorite theorems on the derivative. The theorem is as follows. Theorem. Let f from AB to R closed interval be differentiable, including the endpoints, of course. Differentiable. Assume that f prime of A less than alpha less than f prime of B. Then for some C in the closed interval AB, we have f prime of C equal to alpha. In other words, intermediate value property holds for derivatives. Okay, before the proof, let me state a corollary. Corollary, f prime of x from AB to R cannot have a jump discontinuity. Cannot have a jump discontinuity. Now let's prove the theorem. The proof of the corollary is so obvious that I'm not even going to justify giving a proof. Let's consider this for a moment. We want to show that all intermediate values are taken. So what I do is I simplify the situation. Consider g of x equal to f of x minus alpha x. Okay. Now g prime exists and we clearly see that g prime of A is less than 0 and g prime of B is greater than 0. This just follows because the derivative of alpha x is just alpha. So enough to show that g prime of some C is 0 for some C in AB. Okay, let's look at what g prime A is less than 0 trying to say. Well, since g prime A is less than 0, that means limit h going to 0, g of A plus h minus g of A divided by h is less than 0. And note, because A is the left endpoint interval, h is greater than 0 here. Okay. In other words, for h close to 0 and greater than 0, we get g of A plus h is less than g of A. Okay. In other words, g is decreasing. I'll put this in quotes, near A. So in a later module, once we prove the mean value theorem, we will show that this g is decreasing and the sign of the derivative being less than 0 are intimately related to each other. Similarly, g prime of B is greater than 0. So that means limit h going to 0 of g of B plus h minus g of B by h is greater than 0, right? But here h has to be negative. H is negative simply because we are at the right end point. Okay, so this will just show that g of B minus g of B plus h is greater than 0, or in other words, g of B is greater than g of B plus h. Is greater than g of B plus h. Okay, so net conclusion is that g must attain its minimum in AB. G certainly attains its maximum and minimum in the closed interval AB. It must attain its minimum in the open interval AB. Why is that? Well, because we have found that near the point A, there is a point A plus H such that G of A plus H is less than G of A, and near the point B, we have found a point such that G of B is greater than G of B plus H. So both put together says that neither G of A nor G of B can be the minimum of the function G. So G must attain its minimum in AB. So let's see B in AB be the point of minimum. Be the point of minimum. Okay. Now in the next module we will show G prime of C has got to be 0. G prime of C has got to be 0. Okay, that we will see in the next module. So this will conclude the proof. This concludes the proof. This is a course on real analysis, and you have just watched the module on Darboux theorem.